If I told you there's a version of warp drive that doesn't technically break Einstein's speed limit, would you believe me? Because the weird truth is, modern physics doesn't ban the idea of reaching a distant star faster than light gets there. It bans moving through space faster than light. And that single loophole is where warp drive lives. Here's the pattern interrupt. Warp drive isn't really a drive. It's a proposal to move space itself. In Einstein's general relativity, space and time aren't just a stage where events happen. They're flexible. Mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. That's not science fiction. It's the reason GPS satellites have to correct for relativity to give you accurate locations. So the question becomes dangerously tempting. If gravity can warp spacetime naturally, could a civilization warp it on purpose? In 1994, a physicist named Miguel Alcubierre wrote down an exact solution to Einstein's field equations that did something shocking. It described a warp bubble, where spacetime is compressed in front of a spacecraft and expanded behind it. Inside the bubble, the ship isn't locally moving faster than light. It's basically sitting in a calm region of spacetime. But the bubble itself rides a wave of distorted spacetime, and from the outside, that could make the ship appear to travel faster than a beam of light would through normal space. So when people say warp drive breaks relativity, that's the controversy. It sounds like it should, but the Alcubierre idea is built from relativity's own rules. Locally, no object outruns a nearby light beam. The trick is that the distance between you and the destination shrinks in front of you and stretches behind you. You're not speeding, the map is changing. Now the second pattern interrupt, and it's the part that kills the hype. The original Alcubierre warp drive demands exotic matter with negative energy density. Negative energy isn't just a lot of energy. It's energy that's less than the vacuum. In classical physics, that sounds illegal. In quantum physics, tiny negative energy densities can appear in specific situations. The most famous example is the Casimir effect. Put two uncharged conductive plates extremely close together in a vacuum, and quantum fields change in a way that produces a small measurable force. People sometimes wave this around like, see, negative energy exists. Warp drive confirmed. But that's like finding a single drop of water and declaring you're ready to flood a desert. Because the amount of negative energy you can produce in known quantum setups is unbelievably small, and it's tightly constrained. Physicists like Larry Ford and Thomas Roman developed quantum inequality, limits showing that negative energy is not something you can stockpile freely. Nature allows brief, limited dips below zero, with payback conditions. In other words, even when negative energy shows up, it's on a leash. And the energy requirements? This is where the story gets controversial again, because numbers vary wildly depending on the model, and headlines often cherry-pick the most optimistic estimates. Alcubierre's original calculation implied absurd amounts of energy. Later, in 1999, physicist Chris van den Broek proposed a modification that could drastically reduce the required energy by changing the geometry. The bubble could be microscopically thin on the outside, while containing a larger interior volume. That moved the idea from laughably impossible to still impossible, but at least you can write the number down without crying. Subsequent refinements and different assumptions have produced energy estimates ranging from planetary to stellar scales, often still requiring negative energy densities in some region. Now, here's a big retention twist. Not everyone agrees negative energy is mandatory. In 2021, researcher Eric Lentz published a paper describing warp solitons that, in the math, could be constructed using only positive energy density, no exotic negative energy required. That's the kind of result that makes the internet explode. Warp drive solved. But read the fine print and the excitement gets hit by reality again. The energy demands in those constructions are still enormous, often described in terms comparable to astrophysical scales, and the paper is about whether the equations allow it, not whether engineering can. That same year, Separate work by Alexei Bobrik and Johnny Martiri classified different warp drive spacetimes and argued that, in principle, some warp-like configurations could avoid negative energy in certain senses, but they also emphasized that practical constraints and physical plausibility are a huge deal. Translation: the math is flexible, but nature may not be so generous. So what's the real, honest status of warp drive today? It's a legitimate area of theoretical investigation in general relativity, but it is nowhere near a blueprint for a spacecraft. It's like having an equation that says, you can build a mountain if you can move continents with your hands. The physics doesn't automatically outlaw the shape of the spacetime. It's the required stress energy, the stuff that must exist to produce that spacetime. That becomes the wall. And the walls don't stop at energy. Here's another pattern interrupt. Even if you could create a warp bubble, controlling it could be impossible from inside. In many warp drive models, the front edge of the bubble can form a kind of horizon, similar in spirit to an event horizon. Signals from inside may not be able to reach the front to steer or shut it down. That means you might need to generate and control the bubble from outside, which raises an obvious question. How do you launch a warp bubble around a ship if you need external control? It's like locking yourself in a car where the steering wheel only works from outside. Then there's the issue of what happens to particles and radiation along the way. Some analyses suggest that matter could pile up at the bubble's boundaries, potentially releasing intense radiation when the bubble slows down. Bad news for anyone waiting at the destination. The details depend on the model, but the warning sign is consistent. Spacetime engineering could have violent side effects. And now the most controversial point, because it touches the nerve of time travel. Faster-than-light travel in relativity often comes with causality problems. In certain setups, FTL effectively allows closed time-like curves, paths through spacetime that loop back in time, depending on reference frames and how you maneuver. Warp drive proponents will argue, warp isn't the same as moving through space faster than light. Critics answer, if it behaves like FTL from the outside, causality paradoxes may still arise. This is one reason many physicists suspect nature has chronology protection mechanisms that prevent usable time machines, even if the equations tease them. So where does that leave us? With a paradox that's irresistible. Warp drive is not forbidden by the form of Einstein's equations, yet every known path to making it physical runs into requirements that look beyond our ability and maybe beyond what the universe permits. And that's why serious researchers keep studying it. Not because NASA secretly has a warp ship in a hangar. There's no credible evidence of that. But because pushing on the boundaries of space-time models teaches us what general relativity does and doesn't allow, how quantum fields behave in extreme conditions, and where a future theory of quantum gravity might change the rules. In the past, ideas that sounded purely theoretical, like black holes and gravitational waves, eventually became observed realities. Gravitational waves were directly detected in 2015 by LIGO, a century after Einstein predicted them. That doesn't mean warp drive is next. It means impossible sounding is not the same as impossible. So the real educational takeaway is this. Warp drive is best understood as space-time surfing. The science is real. The loophole is real. The obstacles are also very real. Exotic energy, quantum limits, control problems, potential horizons, massive power requirements, and deep causality questions. If you want more videos like this, where we separate viral headlines from what the physics actually says, make sure you follow/subscribe, because the next episodes will go deeper into how negative energy works, what quantum field theory allows, and what breakthroughs would actually need to happen before any warp concept stops being math and starts being engineering. Now I want to hear your take. If humanity ever builds something warp-like, do you think the biggest barrier will be energy supply, exotic matter, or the universe protecting causality itself?